Hey guys, today let's talk about enthalpy stoich and also about delta H of vaporization and delta H of fusion and how we use those as conversion factors. So, enthalpy is expressed as delta H. So, delta, remember, is a symbol that we use for change in, and the capital H is the variable for enthalpy. So delta H is change in enthalpy, and it refers to the heat of a system or of a specific reaction. So a chemical equation that includes the change in enthalpy is what's known as a thermochemical equation. And if we have that, we know a couple of things about that equation. Because if delta H is positive, then that means our reaction is endothermic, meaning that heat is being absorbed or heat is coming in. And in that case, we can almost think of delta H as a reactant, right? So heat is needed to be added for an endothermic process. On the other hand, if delta H is negative, then that means that our reaction is exothermic, meaning that heat is being released or heat is exiting. And we can think of delta H in that case as being a product or something that is produced. Now, because the relationship between a thermochemical equation gives us a specific amount of energy as delta H and also molar amounts of substances, we can think of delta H as a way of converting between energy and moles of a substance within a reaction. So, for example, if we have this thermochemical equation here, and then we are asked how many moles of carbon are needed to produce 287.0 kilojoules of heat, then we will set this up just like any other stoichiometric conversion, where we have our given 287.0 kilojoules of heat, and we're going to convert into moles of carbon using the relationships from this thermochemical equation, where 1 mole of carbon reacts with 1 mole of oxygen gas to produce 1 mole of carbon dioxide gas, and the delta H would be negative 393.5 kilojoules. Now, since this delta H value is negative, this does tell us that this is an exothermic process. So negative sign means exothermic process. So to set this up, we're going to take our given 287.0 kilojoules, and we're going to set up a factor so that I can get rid of kilojoules and move into moles. Now, because I know that my delta H is this value, this is how I can get rid of kilojoules, because I know that for this many kilojoules, I need exactly 1 mole of carbon, and that is written as the relationship in this chemical equation. So negative 393.5 kilojoules we'll put on the bottom. That way we get rid of the unit kilojoules. And 1 mole of carbon will go onto the top so that we end up in the unit moles of carbon. So this is very similar to using mole ratios to convert from one substance to another within a chemical equation. It's just now we're converting between units of energy and moles of substances within that equation. So a very similar process. So kilojoules will cancel out and go away, and we are now left with moles of carbon, which is exactly what I was asked for. So I am done setting up factors and I am ready to calculate. So 287.0 divided by negative 393. 0.5. So we get this value, and if we look back at where we started, We have 4 significant figures here, so our final answer should also have 4 significant figures. So negative 0.7294 moles of carbon would be our final answer. Now, this is where a little bit of logic comes in, right? So mathematically, this comes out to be negative. However, we're talking about a substance, and it's not possible to have a negative amount of a substance. So we change this to a positive in order to logically make sense. Another way that we can make sure that we end up with a positive value without having to do that extra step of logic is if we think about the wording here. This says produce 287.0 kilojoules. And any time that energy is produced, we can think about the sign as being negative. So another thing that I could have done is to recognize this as a negative 287.0 kilojoules, in which case I would divide by a negative and mathematically come out with a positive. So there are 2 ways to get the correct positive answer here, whether you use logic at the end, like what we started with, to say it's not possible to have a negative amount of something, or whether you recognize that if you are producing this much heat, the sign should be negative, and then mathematically come out with a positive. Either way, as long as you end up here, you've done correct. To look at another example, let's look at this reaction. So how many grams of hydrogen bromide were produced if 156.8 kilojoules of energy were absorbed in the reaction 1 mole of hydrogen gas reacting with 1 mole of bromine and absorbing 72.80 kilojoules of heat to produce 2 moles of hydrogen bromide? Okay. So, since this says energy absorbed, I can think of the sign here as being positive. So 156.8 kilojoules of energy absorbed, positive sign. Now, ultimately, I need to convert between those kilojoules of energy into grams of hydrogen bromide. So I want to factor out my kilojoules, and according to my equation here, there are 72.80 kilojoules of energy needed for this reaction as written. And this is written as a reactant. So if you remember, if delta H is a reactant, then the sign is positive. So I am going to leave that a positive 72.80 kilojoules. And for every 72.80 kilojoules, there are 2 moles of hydrogen bromide produced. Now, my problem asks me for grams. So I don't want to stop here. I want to keep going until I get to grams. So I can convert between moles and grams by using the molar mass. And the molar mass of HBr can be calculated by adding up the molar mass of hydrogen, 1.008, plus the molar mass of bromine, which is 79.904. And we add those up, and we come up with 80.912 grams per mole of HBr. So now that I'm in the unit that I was asked for, I'm ready to calculate. And if we go back to the start, I'm going to need 4 sig figs. So when I calculate and I round to 4 sig figs, 348.5 grams of HBr is my final answer there. So when you are given a thermochemical equation, you can treat the kilojoules or the delta H value, the enthalpy of reaction, just as you would any other mole ratio between substances. And that allows us to convert between kilojoules and moles of any substance within our equation. But if I don't have a thermochemical equation, there is another way that I might be able to convert between moles and kilojoules of energy. And that is by using delta H of fusion or delta H of vaporization. So delta H of fusion is the molar heat of fusion, or the energy that is required to melt 1 mole of a solid substance. On the other hand, delta H of vaporization, or the molar heat of vaporization, is the energy required to vaporize or boil 1 mole of a liquid substance. So both delta H of fusion and delta H of vaporization can be used as conversion factors between kilojoules and moles because the units of both of these two things are kilojoules per mole. So for an example, if I wanted to know how many kilojoules of heat would be absorbed when 340.0 grams of ethanol vaporizes at its boiling point of 78.0 degrees Celsius, I could do that conversion simply by knowing that the enthalpy of vaporization for ethanol is 39.3 kilojoules per mole. That is because what this is telling me is that it takes 39.3 kilojoules of energy to vaporize exactly 1 mole of ethanol, which is C2H5OH. So this unit can be written out like this, in which case this becomes our conversion factor between moles and kilojoules. So even if I don't have a thermochemical equation, if I know the delta H of vaporization or the delta H of fusion, I can still do conversions between moles and kilojoules. So for this example, we're starting with 340.0 grams of ethanol. And we ultimately want to know how many kilojoules of heat are going to be absorbed. Now, we are told that the boiling point is 78.0 degrees Celsius, but that's just extraneous information. It just tells me that we're at the boiling point and the boiling is going to happen. Doesn't tie into our problem here. So to go from grams to moles, we're going to need our molar mass of ethanol. So quickly calculate that. There are 2 carbons plus 6 total hydrogens plus 1 oxygen. So molar mass of ethanol is 46.069 grams of ethanol for every 1 mole of ethanol. And now I can use my delta H of vaporization to convert from moles into kilojoules. 1 mole of ethanol requires 39.3 kilojoules of heat to vaporize. And since my question asked me for kilojoules, this will leave me in kilojoules, so I am ready to calculate. I'm going to need a total of 4 sig figs in my final answer. So let's quickly calculate this. $290.0 kilojoules would be needed to vaporize. One last example for today. How many joules of heat energy would be required to melt 175 grams of aluminum metal at its melting point of 660 degrees Celsius? And the enthalpy of fusion of aluminum is 10.7 kilojoules per mole. So we're going to be converting 175 grams of aluminum into joules. So 175 grams of aluminum. We'll use our molar mass to convert from grams into moles. So aluminum's molar mass is 26.982 grams of aluminum for every 1 mole of aluminum. Now my delta H of fusion tells me that for every 1 mole of aluminum, it takes 10.7 kilojoules of energy to melt it. And this time I am asked for the unit joules. So I need to convert from kilojoules to joules. So 1 kilojoule is 1,000 joules. And ultimately I will need 3 sig figs here. So let's calculate. So mathematically, I get this value. So 69,398.12 with a couple more decimal places after it, joules. But remember, I need 3 significant figures. So I have 2 choices. I can round to 69,400 joules, and that would be 3 sig figs. Or I can put this in scientific notation, in which case it would be 6.94 times 10 to the 4th joules. So either of these would be just fine.